Y18 electromagnetic waves. First, let us review elementary terminologies of wave. Frequency, 1 over period. Angular frequency, omega. It is identical to nu. We have to multiply to pi because one cycle has the angle to pi. Just like what we have done with from the frequency to angular frequency, it is convenient to have a multiplicative factor to pi in the case of wavelength. Then we define the wave number k, that is 2 pi over lambda. And actually, the wave is a kind of x minus vt, something like that. But this function, simplest wave, is just a sinusoidal function. And this has a bad normalization. It returns to the same point only if x equals to pi. And this is the dimension is wrong. Why? Sine something must be dimensionless. So the best way is x must be scaled with its own wavelength, and time must be scaled with its own period. It becomes the dimensionless. So what is the best combination of the two dimensionless number that can be substituted as an argument of a sinusoidal function? Is that, okay, 2 pi is the best one. Why? The simplest, the best, this is simplest expression. It returns to the same position when we shift x by lambda. It returns to the same position when we shift time by period. So this is the simplest choice. If we rewrite this one, sine kx minus omega t, and just copy 2 pi over lambda, omega, 2 pi over period. That's it. Okay. Then what is the speed? F of kx minus vt. Okay, rewrite this one. Factor this 2 pi over lambda. Then it is x minus 2 pi lambda and t 2 pi t. Cancel, cancel. Aha, what's that? This is vt. V equals to lambda over period. And this lambda over period can be expressed as this. What's this? This is omega over k. So V is omega over k. And this is a carbon copy of this relation. And then why don't we extend this idea to the motion of a wave in 3 dimensions? In 1 dimension, this is like that. Time has a single component. We don't modify this, but we have 3 components in space. So kx, simplest expression for kx is just k vector scalar product with x. In here, k vector is along the x-axis only. Aha. So k, in general, k must be expressed as k1 e1, k2 e2, plus k3 e3. That wave vector. If it is just a one-dimensional case, we use the wave number. But if it is a three-dimensional vector, Euclidean vector, then we say it is a wave vector. So wave vector squared satisfies the same relation as a wave number squared. Okay. Next. Sinusoidal function is the simplest choice for a monochromatic wave. Monochromatic wave is purely lambda and it is purely period t. Single period, single wavelength wave is called a monochromatic wave. However, as we have done with the circuit analysis, you remember substitution of sine omega t plus delta cosine omega t minus the delta, something like that. What was better? This was better because the sine, cosine, when I take the derivative, it becomes sine becomes cosine, cosine becomes sine, and the plus minus sign differs. I just complicate it. I don't like it. Simplest choice is exponential I omega t. And at the end of the day, if you began with the sine, why don't you take the imaginary part of e to the I omega t? If you began with cosine, you start with e to the I omega t, and at the end, you take the real part to reproduce cosine. That's it. So let me simply make use of exponential I kx minus omega t for a trial function for representing the propagating electric field. Here, k wave vector is the sum of three components. Let's review the partial derivatives. You have been unhappy with dealing with many differential calculus in previous class, but now you will be happy with because that your previous work is a very nice tool to deal with this kind of calculations. So let me pass this. This one reads coefficients minus IB and IC. Okay. Why don't we take the gradient? Usually gradient is applied to scalar field, but it doesn't matter. Let me apply gradient operator to the electric field written in here. What's that? It collects the coefficients IK1, IK2, IK3, and it doesn't care about omega t. The final result is if I take the gradient, it reads the coefficient of x dot, effectively this. Next, we consider apply Laplacian operator. And Laplacian is defined by actually divergence of a gradient. So that is x1 squared double derivative, x2 double derivative, and x3 double derivative. So the answer is ik1 squared, ik2 squared, plus ik3 squared. That's minus k squared. Simple. So if I take the time derivative, I need to pull out minus I omega here. And the time derivative always accompany speed of light because gradient is 1 over length. Time derivative is of different dimension. Correct dimension is to include the speed of light. That is 1 over length. So spatial derivative and time derivative accompanied with 1 over c have the same dimensions. So using this way, the time derivative with the c will give this factor. And if I do twice, I have minus omega squared over c squared. We know this one very well in the previous calculation with the wave number. So let me copy this result and this result. What we find in here from this and this relation between these two coefficients, I can say the electric field, this one, is a solution of a wave equation. Okay? So electric field is a wave equation, satisfy the wave equation with the speed of light. So electric field travels with the speed of light, and if I do the same job with the magnetic field, magnetic field also travels with the speed of light. However, this one is in general complex number, so that there should be some phase difference. We remember R, L, C, they have a phase difference. Just like that, we have to worry about the existence of non-vanishing phase difference between the electric field and magnetic field. But Maxwell's equation tells us everything. First, these are two Gauss law equations. Right now, I'm worrying about the propagation of electromagnetic field in vacuum. Forget about charge, forget about current. From this, substitute these two. Divergence will give what? Divergence will give k dot. So ik will appear, will be replaced in here. There is a scalar product with the wave vector and the amplitude for the electric field. Divergence B also brings ik. So wave vector scalar product with the amplitude vector for the electric field and the amplitude vector for the magnetic field. This is a very important result. We know both of them are zero. Scalar products are zero. What's that? Propagating electric field is perpendicular to the wave vector that is parallel to the direction of propagation. Magnetic field is also perpendicular to the direction of propagation. Very, very important. That means electric field, magnetic field, electromagnetic field is a transverse wave. But at this moment, still we don't know the relationship between electric field and magnetic field. The relationship between them can only be obtained from Faraday's law and Maxwell's law. Let's do that. This is the one. And this is the one. But we don't care about not displacement current. Displacement, we have to care about the displacement current, but we don't want to consider actual current because we are in vacuum, no charge, so no rho, no J. However, JD is not a physical current, it is just the time-dependent electric field. So we concentrate on these two coupled equations. However, it's not very difficult. We know the trial solution. We substitute this trial solution to these two equations of motion for the electromagnetic field. Previously, we have obtained that they are transverse wave, that they are perpendicular to the wave vector k. Next, we take the car, that means IK appears in here, IK cross E. And here, minus 1 over C, and time derivative will give minus I omega. So this minus minus becomes a plus, and I cancels. So we end up with this relation. This is over a factor. It's better not cancel this speed of light, but cancel the magnitude of k and magnitude of omega over c. They are the same. So we arrive at, if I write this k vector as wave number multiplied by unit vector, what we find is this. What's that? We know the electric field is perpendicular to the wave vector. So wave vector k, that is parallel to n hat, and electric field is in this direction. They are perpendicular. However, n cross e, that has the direction. So three vectors are all perpendicular to among one another. In addition, this is a unity. Therefore, the magnitude of the electric field is identical to the magnitude of magnetic field multiplied by the speed of light. So CB magnitude is the same as the electric field. Maxwell is a genius. He has found everything. And electric field, magnetic field multiplied by the speed of light and the unit vector along the wave vector constructs the basis set of the Euclidean space, and these three vectors construct the triad E1, E2, E1, E2, E3. Mathematician can never tell you how to bring three unit vectors in nature. Maxwell told us what's the basic entity in nature to construct the Euclidean space. It is not from mathematics textbook, but the changing electromagnetic field determines the three-dimensional space. It is a marvelous discovery. Now, you don't see any phase difference in the cancellation of these two factors, kx minus omega t, e to the I kx minus omega t plus delta. This delta must be 0. So electric field and magnetic field are in phase. This delta must not be there. They are in phase. We call it is a polarization vector. Polarization vector of electric field and magnetic field. Among these four contributions, only two of them are linearly independent. Once you know E1 and E2, B1 and B2 are completely determined by the Faraday's law and Maxwell's law. So, in nature, electromagnetic field has only 2 degrees of freedom. Interestingly, light travels with the speed of light, and electromagnetic field has a speed of light, and for electromagnetic field, the space is not 3-dimensional because of the complete length contraction of space from minus infinity to infinity is frozen into a pizza. We have only 2 dimensions that are represented by two polarization vectors of the electric field. And in addition, we learned very much parallel plate capacitor has its own electric field energy. And you have solenoid. Inside the solenoid, you have magnetic field energy. And these two field energies are written in the form However, this expression is historically wrong. Its correct expression should be of the same dimension as electric field. If I write in this way, then we have 2 mu 0, and this one, c squared, must be canceled. You know 1 over c squared equals mu 0 epsilon 0. That mu 0 epsilon 0 kills this one, and what's that? We have a common factor. As you know, the two electric field and magnetic field multiplied by the speed of light, they have the same amplitude, and they are delta? No, they are in phase. So Poynting vector is nothing but the sum of this electric energy saved inside the electric field and magnetic field energy. Sum of this magnetic and electromagnetic field energy multiplied by the speed of light. Okay, so that is actually current density of electromagnetic field energy. So energy deposit per unit area per unit time due to the propagating electromagnetic field is simply represented by Poynting vector. Okay? And this is the calculation with the amplitude only. So this, I think you can read it through by yourself, but let me explain what's going on here. Speed of light c represent the propagation of speed of electromagnetic wave. Yes, Einstein's special theory of relativity states that speed of light is invariant in any inertial reference frame. Actually, our four equations of Maxwell contains the speed of light. If I apply Galilean transformation to differential operators, what we find? The equation for a wave propagating with the speed of light after Galilean transformation, very strange piece appears. So it is not physics. I mean, according to Galilei, on the Galilean transformation, F equals ma is invariant. However, on the Galilean transformation, Maxwell equation transforms into different equation. In that case, we don't have to learn physics anymore. That means that's the wrong physics. That means Galilean transformation does not work for the electromagnetic field because electromagnetic field is traveling with the speed of light, and Newtonian mechanics cannot tell you anything about the particle's motion that is moving with the speed of light. This is a complete breakdown of Newtonian mechanics, and we need something new. That is the relativity introduced by Einstein. And Lorentz transformation was obtained, derived, well before the Einstein's trial. However, they didn't know that that Lorentz transformation keep this operator the same. That means under Lorentz transformation, Maxwell's four equation keeps the speed of light, c, as the same, and all theory becomes a beautifully invariant, just like F equals ma is invariant under Galilean transformation. That's the reason why we learn later in the semester special theory of relativity of Einstein, because this is a basic fundamental frame on which electromagnetism is standing on. And electromagnetism is the basis of all physics, current contemporary physics, and engineering. Okay.